In this video, we will discuss real numbers. Real numbers are used in everyday life to describe quantities such as age, miles per gallon, container size, and population. They are represented by symbols such as. So, some examples of real numbers include the number 5, -9, 2/3, 0.333 repeating, 6 squared is a real number. The cubed root of -32, and also numbers such as pi. So all of these are real numbers. So let's talk about real numbers. Real numbers can be divided into smaller subsets of the real numbers. So some of our larger subsets are rational numbers and irrational numbers. So a rational number is a number that can be written as a fraction. So some examples here. I could write -6 as a fraction. 0 can be written as a fraction. 2/3 is obviously a fraction. I could write 1.3 repeating as a fraction. 1.25 could be a fraction. And I'm sure you can think of other numbers such as 5 that also could be written as a fraction. In contrast to rational numbers, before we take a look at the even smaller subsets of those, we want to take a look at the irrational numbers. So these are numbers that cannot be written as fractions. But the way that we'll describe them is numbers that have decimals that do not repeat or terminate, meaning they don't end. Some of these values you can recognize, such as pi, but we can also make these numbers up. So we could have like 3.9172564 ... right? So that's going to go on forever and ever, but it's not repeating. Other values include the square root of 2. Okay? That is an irrational number. We cannot write that value as a fraction. So let's go back to our rational numbers now. So we see kind of a variety here in those rational numbers as far as what numbers can be written as a fraction. Okay? Our next largest subset is integers, and these are positive and negative whole numbers. Okay, so positive and negative whole numbers, we're looking at things like -5, -10, 0, 5, 10, 100. So positive and negative whole numbers, okay? And don't let things confuse you. They might give you, sometime you might see 4/2 and be asked to classify that. But since 4/2 simplifies to 2, it is also an integer. Whole numbers. Whole numbers are the set of numbers that start with 0. And we can write this as a set as so 0, 1, 2, 3, 4, 5, and so on. Those are whole numbers. So again, here we have no negatives and no fractions. Unless the fraction would be something like 10/5, which would simplify to 2. And finally, we have natural numbers. These are also sometimes called counting numbers. These are the numbers that make sense to you, that feel natural, the ones that you learn to count. So they start with 1, 2, 3, 4, and they continue on. Again, there are no negative values for natural numbers. If we take a look at these real numbers, especially the rational numbers, notice how natural numbers is inside the whole numbers box. That means that all the natural numbers are also whole numbers. And it means that all the whole numbers, except for 0, are natural numbers. Moving up, we see that the natural numbers and the whole numbers are both inside the integers box. That means that whole numbers and natural numbers are also integers. Since the integers is inside the rational numbers, then that means that integers are also rational numbers. And since whole numbers and natural numbers are smaller groups of integers, they are also rational numbers. Rational numbers and irrational numbers are all real numbers. So we will work a little bit in the future with classifying real numbers and ordering real numbers. So now that we have a thorough understanding about what real numbers are, we can talk about ordering real numbers. So this is putting numbers from least to greatest, or greatest to least, or having some specific order for those numbers. So if A and B are real numbers, A is less than B if B minus A is positive. So what this is saying is A is smaller than B if when we take B minus A, we get a positive value. This is something that we've been doing for many math classes now. The order of A and B is denoted by the inequality A is less than B. Here we have your standard number line. So we have 0. 0 is going to be our origin. Okay, we have not moved yet into the coordinate plane where our origin is the intersection of the x and y axes. Here we just have that one axis, so our origin is 0. To the right we have positive numbers, to the left we have negative numbers. So as far as that inequality A and B, where we have A is less than B, A is going to be less than B if it is farther to the left of B. Here we will look at interpreting inequalities. So describe the subset of real numbers represented by each inequality. And we'll do that by graphing it on the number line. This should not be anything new to you. So we want all of the values for x that are less than or equal to 2. Notice here how we have that equals part. That means we're going to have a bracket at 2. This is corresponding to that closed circle that you were probably used to from previous algebra classes. Here we're going to replace it with a bracket, and you will see more information about that later on in the video. Here we're concerned with all of the values that are less than that, so we are going to follow this to the left. So this is how we describe that subset of real numbers represented by this inequality. X is less than or equal to 2. Next we have -2 is less than or equal to x is less than 3. Here we have the less than or equal to. Remember, that would be a closed circle, so it's going to translate to a bracket. The less than 3 would be an open circle. It's going to translate to a parenthesis. So we'll have a bracket at -2, a parenthesis at 3, and here we have, since the x is between those values, our x is going to be bound in between them on the number line as well. So we want all of the numbers between -2 and 3, including -2. So some intervals on the real number line are going to be bounded. And what that means is that we have a smallest value and a largest value, neither of which is infinity. So these are no infinity. You'll see here a bit of a difference in your notation. And the difference is really just with the graph. So you've seen before the notation where the square brackets note your interval from A to B. And we've called that a closed interval. And we've always used this with closed circles. Here we're actually going to take those same brackets and place them on the number line. And the same thing with parentheses. So if we look at the open interval type and we see from A to B, that interval, here we are not including those endpoints A and B, but again, we just have parentheses at the A and B. In the bottom two, you can see that we can mix and match those depending on what our inequality is and how our interval is working. So we can include the left endpoint but not include the right endpoint, or vice versa. Unbounded intervals on the real number line. So these always include infinity. So a few things that we need to note here is any time in that notation that you are looking at the infinity symbol, you always see a parenthesis. So infinity always has a parenthesis. It will never have the square bracket. So how do we know in our graph that we're going off to infinity? We just only have one bound for the most part. So if we look at our top interval, where we have from A, and we're including A, to infinity, okay? This is all of those values for x that are greater than or equal to A. So everything that's bigger than A. Looking at our graph, since we are including A, we have the square bracket, and then we are going off in the direction of positive infinity indefinitely. With our second graph, here we are just not including A, okay? With our third and fourth graphs, we're going off to negative infinity. So here we have a highest value of B, and we are looking at all of those values of x that are less than B, heading toward negative infinity. Finally, our last interval includes the entire real number line. So that's going from negative infinity to positive infinity. That's all of the real numbers. So here we don't have any bounds at all. We're just highlighting the entire number line. We can use inequalities to represent intervals. So here we are being asked to use inequality notation to describe each of the following. So number one, C, or letter A. C is at most 2. That means that C is no bigger than 2, but C can be 2. So we have that equality part, and we want no bigger, which means less than. So this is C is less than or equal to 2. In example B, we have M is at least negative 3. So here we have M and negative 3. And we know that M is at least negative 3. Well, if we had at least $5, then we would have $5 or more dollars. So we would have greater than or equal to $5. So if M is at least negative 3, we'll have that M is greater than or equal to negative 3. Example C, all x in the interval from negative 3 to 5. And I know with this font, this is a little bit difficult to see. This is actually parenthesis negative 3, comma 5 with a bracket. So we want to write this using inequality notation. With this, we can simply write our negative 3 and an x and our 5, leaving spaces for the inequality symbols that we need. Note that this parenthesis is going to tell us that we can go to 3, but we don't want to equal 3. However, the bracket tells us that it's okay to equal 5. So our final answer is negative 3 is less than x is less than or equal to 5. In interpreting intervals, we are asked to give a verbal description of each interval. So interval A, we have negative 1 to 0. This would be all values greater than negative 1 And because it's a parenthesis, it is strictly greater than, not greater than or equal to. And less than, again, for the same reason, 0. So all values greater than -1 and less than 0. Looking at B, we have -2 to infinity, but we're including -2. Notice how we're going off to infinity. When that happens, we can simply write all values. And for this case, this is greater than or equal to 2. And we have no bound on that right side. So we're going off to infinity. We don't have anything else to write there. Let's look at C. C is similar to B. However, C goes from -infinity to 0. And we note that both of these are parentheses in this situation. So if we were graphing this, we would have a parenthesis at 0, and we would be going off to the left toward -infinity. So these are all of the values that are less than 0. They're not equal to because it's a parenthesis, not a bracket.